Hi, good afternoon, residents from Brazil. Good evening, good morning, according to where you are around the globe. I'm actually very happy to say for all of you that we have more than 56 countries following the seminar, which is a great number. And you are all very welcome to the second week of the International Virtual Seminar on Wood, Pulp, and Biorefinery of the Federal University of Viçosa. And I hope you all enjoy the session, interact with the speakers, and acquire as much knowledge as you can. I'd like to announce myself. I'm Felipe Pedersoli, chemical engineer, postgraduate student of the University of Viçosa, member of the organizing committee of this event, and also the moderator for today's session. I would like to thank the other members of the organizing committee, Professor Yara de Muné, Professor Ana Márcia Ladeira, and Marcelo Coura, who helped a lot in the organization of this event. The moderators, Professors Rubens Chaves and Claudio Mudado, for all the speakers and all of you who are watching from the most diverse countries. I'm very proud to announce today's speaker, Bruno Gonçalves, who will deliver the lecture Optimizing Three-Stage Bleaching Sequence for Eucalypt Kraft Pulps. Bruno, thank you for accepting the invitation. Bruno is a chemical engineer with more than 4 years of experience working as a process engineer. He has worked at Brazilian pulp mills, mostly focused on kraft pulping and bleaching optimization. He currently works as a process optimization service engineer at Valmet Automation. Actually, very actual this information because he just started his work in this new company in 1 week. Thank you again for accepting, Bruno Gonçalves, and the speech is all yours. Hope you all have a great event tonight.
Thank you very much, Felipe, for the introduction. So good evening or good afternoon, everyone. I hope you enjoyed this lecture, and you can ask questions at the end of the lecture. So I hope you all enjoy. So the topic is optimizing three-stage bleaching sequence for eucalypt kraft pulps. So let's get started. So the objectives and challenges in pulp bleaching. So we want to produce high quality fully bleached pulp, 89 to 91 ISO brightness, high brightness stability, good viscosity, pulp strength. We want very clean pulp, so not much chives and other foreign material. We want bleaching to be cost effective. That's the main point when you have a bleach plant. We, of course, want low environmental impact and, of course, maximize production rates. Just so we get on the same page, some terms and concepts that you need if you want to really understand this lecture. So most of you must know this, or if you don't, that's a good opportunity to learn. So some units here. If you go from bone dry ton or oven dry ton to air dry ton, which is the most common in Brazil. So if you wanna convert these units, if you're in kilograms per bone dry ton to kilograms per air dry ton, you just multiply by 0.9. So that's pretty easy. If you do the opposite from air dry ton to bone dry ton, it's easy as well. It just divided by 0.9. So you make sure you never miss that again, because most papers really don't show how to do it because it should be basic, but sometimes you can get lost. You can also express chemical charges as percent on pulp. So what it means is that it's the percent of applied chemical on bone dry or oven dry pulp. So if you want to go from kilograms per bone dry ton to percent on pulp, you just divide by 10. That's pretty easy as well. So from percent on pulp to kilograms per bone dry ton, you just multiply by 10. So those calculations, you can use a lot of them on papers, on research, or at mills. If you go from a mill to another, you can really easily convert units. That's important, not to miss those. Okay, so one example here. 0.4% of hydrogen peroxide or any other chemical. So from this percent to kilograms per bond dry ton, it just multiplied by 10. So from 0.4 times 10, you have 4 kilograms per bond dry ton. So that's easy calculation. So if you want to go from kilograms per bond dry ton to air dry ton, so if you have 4 bond dry ton here, you just multiply by 0.9 and then you have 3.6. So just for you to know this type of calculation, that's important. Also, we have active chlorine, which is a very common concept. It's the common basis for bleaching oxidizing agents. So the calculation is just you get your chlorine dioxide times 2.63, and then you have your active chlorine charge. So from also the peroxide, you multiply by 2.09, and you have your active chlorine as well. Also, there is the total active chlorine, TAC, which is the sum of chlorine dioxide and peroxide as active chlorine. So, for example, a meal dosing 10 kilograms per bond dry ton chlorine dioxide and 4 kilograms per bond dry ton peroxide, you just get your 10 kilograms times 2.63 plus 4 kilograms times 2.09, and then you have 34.7 active chlorine per bond dry ton. So it's important calculation. Also, you can get from bond dry ton, so 34.7, if you divide by 10, then you have 3.47% chlorine on pulp. Also, some other important concept. First is the Kappa Factor, which basically you have your active chlorine dosed to the D0 stage. That could be, for example, the hot stage. So then you have as percent chlorine on pulp, and you divide it by your inlet kappa number to the bleach plant. So usually it's your post O2 kappa number if you have O2 stages, but here we are discussing eucalyptus pulps, 3 stages, so it's your post O2 kappa. So kappa factor, we're gonna talk a lot about it. Also, we have the total kappa factor, which is your total active chlorine divided by your inlet kappa to the bleach plant. So it's the same kappa here. So kappa factor is just your charge to the D0 stage divided by your kappa, and total kappa factor is your total active chlorine divided by your kappa number. So selectivity is also an important concept here. It is the degree to which lignin and or hexa can be removed or modified versus the degree of degradation of the pulp. So, for example, selectivity can be your delta kappa divided by your delta viscosity, or your delta hexa divided by your viscosity, or your delta brightness divided by your delta viscosity. So it's how much you gain your brightness, or you remove kappa or hexa divided by your viscosity loss. So just to show you what a modern ECF fiber line is from Valmet. So here we have a compact cooking digester with an impregnation vessel. You have brown stock screening. You have the wash presses here, which is brown stock washing. Then you go to your oxygen delignification stage. Then you have wash presses again. It's your post O2 washing. And then you have basically 3-stage bleaching, which is very common for eucalyptus pulp. So you have your hot chlorine dioxide stage, D hot, and then you go to your extraction stage with peroxide, EP, and then the final D stage, which is D1. So I'm gonna tell you a little bit about the Exynoic acids and their impact on Eucalypt pulp bleaching, because that's the main difference between kind of softwoods and hardwoods. It's really, really different because you have a lot of Xa on hardwood pulp, especially eucalyptus. So here we have the kappa number after pulping. You can see here that there's a lot of lignin, but also a lot of Xa and some of others. So when you exit O2 stage, which is oxygen lignification, you have Xa and lignin. They're both reactive towards oxidizing chemicals. So they both can consume oxidizing chemicals. But here you have that Xa can be removed by acid hydrolysis, which is an advantage. So you don't waste your oxidizing chemicals with Xa. And so here you have, of course, lignin that you need oxidizing chemicals. So can remove lignin. And of course, here you can see that the Xa content is really high. It's about 5 kappa units, maybe a little bit more on your post O2 kappa number. So you know that Xa, they're colorless, but they contribute to kappa number. They react with hypochlorous acid, and chlorine. So hypochlorous acid is generated from chlorine dioxide during bleaching reactions. So Xa, they consume chlorine dioxide, which was intended for the lignification brightening reactions. So bleaching reactions mainly in these stages. So you kind of consume in your overall bleaching sequence around 0.15 kilograms of chlorine dioxide per Xa units per dry ton. So that's a lot of chlorine dioxide. And we know that if we don't remove the Xa, they cause a brightness reversion in the final bleached pulp. So bleaching of eucalypt pulps, usually 3-stage, suffice for up to 91% iso brightness. But those 3 stages, they must contain an acid hydrolysis or hot chlorine dioxide stage to be feasible and cost effective. If you don't include this kind of stage, Xa are eventually removed, but at higher cost of oxidizing chemicals, for example, your chlorine dioxide. So nowadays we have a lot of different modified bleaching sequence for Xa removal. They provide savings in your chlorine dioxide. They give you lower brightness reversion. So the most famous ones are the D-hot stage. It's the hot chlorine dioxide stage. And also you can use a hot acid hydrolysis stage followed by a D stage, or regular D stage. So here we have a typical 3-stage sequence. So first stage is a D-hot stage, a hot chlorine dioxide stage. It's very common. So then you go to your alkaline extraction with peroxide stage, your EP, and then your final bleaching stage, your D1. So we're mainly going to focus on these sequences. But of course, the mindset can be applied to any sequence if you just understand what I'm telling you here. So let's discuss about the hot chlorine dioxide stage, or D-hot, which is the first stage of bleaching. So it's really important that you really understand this so you can have a good overall bleaching performance. So basically, the hot stage, you get a wash press, also to washing, then a pump. So your pump goes through a mixer, you have steam. Other mixer, you add your chlorine dioxide. You can have an upflow tube and then a bleaching tower here. So an upflow and then downflow. Of course, this can change as an example, and then you pump it to wash presses again, so you can go in the next bleaching stage. So the D-hot stage is basically a hot acid stage for acid hydrolysis, combined with a D0 stage. So we know that reaction rate with chlorine dioxide, of chlorine dioxide with lignin is much faster than with Xa's. So this is an advantage. So most of your chlorine dioxide, when you add it, reacts rapidly with lignin. So it is consumed in the beginning of the reaction. And then your Xa are removed later through acid hydrolysis at very high temperature and very long residence time. So a D-hot stage is much more efficient to reduce the kappa number than to increase brightness, mainly because hypochlorous acid and chlorine are very efficient for delignification, so to remove lignin and to remove Xa, but they're not very good for brightening. They have really low brightening action. So the main objective of your D-hot, of course, you have to increase your pulp brightness, and you will, but mainly you need to remove lots of lignin and Xa. So before you look at your D-hot performance, first you need to understand that D-hot brightness and kappa number, so at the exit of the D-hot state, they're not real performance variables, so don't be deceived by it. Mainly because some oxidized compounds, they're not soluble at low D0 stage pH, but then they are soluble at high pH in extraction stages. So usually full delignification and brightening effects of a D0 stage are not fully noticed until the pulp is extracted. So after it goes through an extraction stage. So alkaline extraction sometimes levels out, so equalizes apparent differences noticed after D0 stage. So the real performance of a D-hot stage is measured after your EP stage. So always look at your D-hot and EP stage combined. Do not look only for the D-hot stage. Look at both stages. Here's an example. I have some data here from the literature that shows here you have your D0 brightness. So at the exit of the D0 stage or the hot D0. So here, for example, you see that from a Kappa factor 0.22 to 26 and 0.3, you see here that it looks like you're getting a brightness increase here of about 2 points from 70 to 72. But then if you look at your EP brightness, here's just 0.4 ISO brightness. So if you look at your D0 brightness, you imagine that that extra chlorine dioxide is being really good for you, but actually it's about the same brightness and you're putting lots more of chlorine dioxide. So this is deceiving. This D0 brightness is deceiving. So look at the EP brightness. So always look at both stages combined. So here are some variables that affect a D-hot stage. So your inlet kappa number usually is around 8 to 12. Your Xa from 40 to 75. Your chlorine dioxide dose, which is your, mainly we look at the Kappa factor that I explained before. So it's 0.10 to 0.30. You have your carryover, which is the organic and inorganic material that you carry from postal to washing to your D-hot stage from 5 to 20, residence time from 100 minutes to basically 3 hours. You get your temperature from 85 to 96 degrees Celsius. your final pH, usually from 2.5 to 4, and your consistency, so media consistency around 10 to 12. But you have all those variables, but the variables that we can really optimize is your chlorine dioxide dosage that you use the Kappa factor. So usually from 0.10 to 0.30, and then you have your final pH from 2.5 to 4 and your temperature from 85 to 96. So let's discuss about the Kappa factor, which is really important. So your D-hot Kappa factor, here's how it impacts brightness. So as you increase your Kappa factor, you see here that your EP brightness also increases. So as you increase your Kappa factor, you get a larger brightness increase. So you can really increase your brightness from, for example, 78 to 83 by increasing your chlorine dioxide charge. Also, here's the impact on the EP kappa number, so the post-extracted kappa. So as you increase your kappa factor, similarly to what happens to brightness that increases, here you decrease your kappa number. So it shows that you're removing lignin and Xa maybe. So as you increase your Kappa factor, you decrease your Kappa number. Here we have the Kappa factor impact on your viscosity measured after extraction. Of course, everything here is measured after extraction. So as you increase your Kappa factor, you also decrease your viscosity. So basically, the effects of increasing your Kappa factor, as I showed you previously, you get higher brightness, you lower your Kappa number, but you also get lower viscosity. So then you ask yourself, do I apply very high Kappa factors? If I told you that you get higher brightness, you get lower Kappa number, you get lower viscosity, but you can deal with that maybe. So then it's a really good question. Lots of people, they put lots of chlorine dioxide in their D-hot stage. So is it really what you should do? Maybe not, because think that you have 3 bleaching stages and 2 of them are chlorine dioxide stages. So when you look at this, you don't really get a very high Kappa factor. You have to look at costs, quality. So you got to apply the most effective Kappa factor, not the highest Kappa factor. Basic rules for the hot stage Kappa factor are you should consume all your added chlorine dioxide, so you should react to 0 residual. The minimum Kappa factor is around 0.12. That's pretty low, but you shouldn't go really 0.10 or 11. You start from 0.12. That's pretty good. So the rule is that you should achieve sufficient delignification and brightening as well. You should arrive to a Kappa factor, a Kappa number after EP stage, maximum 3.5. So usually 1.8 to 2.5, maximum 3.5. In your EP brightness, you should get higher than 80 ISO brightness, usually from 81 to 86. And the maximum Kappa factor is usually around 0.28. You shouldn't go above 0.28 usually. So you should avoid overdosing. And usually you should try to get your Kappa factor lower than 0.22 for an inlet Kappa of around 10 and lower than 10. So if you have a lower than 10 Kappa number, don't go much over 0.22. And also, you got to notice that the hot stage temperature and residence time, they allow higher chlorine dioxide consumption than, for example, a conventional D0 or hot A followed by D0 stage, because they have much lower residence time. So when you think about your optimum kappa factor, you should look at your incoming kappa, your brightness, incoming brightness, and your target final quality. So what is the final brightness that you expect? So your total chlorine dioxide should be always the lowest possible, but you need to achieve your target quality. So you cannot go too low, then you lose your quality. So it has to be the lowest possible to achieve on target quality. So the challenge with the optimum kappa factor is really to distribute chlorine dioxide between the D hot stage and the D1 stage. So the D hot is for delignification, and the D1 is just for brightness increase, which is brightening. So you also have to select your optimum target EP kappa and brightness. So you select kind of which is the best EP brightness that I can get, kind of the lowest chlorine dioxide charge possible. But be careful, if you go for a too low kappa factor, you get insufficient delignification, you get a high post extraction kappa and very low brightness. This will require extreme brightening conditions in EP and D1 stages. Your total chlorine dioxide will increase because you'll have to put a higher charge to the D1, and you may compromise your final quality. But also, if you go for a too high kappa factor, this will be overdosing, this will be inefficient, because you get a too low EP kappa number. So your EP kappa number will be too low. This will mean that you have exaggerated a lignin Xa removal. This will cause you a viscosity impairment, which is really bad. And also, there's not much brightness increase above certain kappa factor. So as you increase your kappa factor, you see that when you arrive at a certain point, there's no much more brightness gain, mainly because there's not much lignin to be oxidized. When you're dealing with eucalyptus pulp, there's not much lignin when you arrive at your D hot stage. And this lignin is highly chlorinated, so it means that it has very low reactivity. So you must go through an extraction stage to get it activated again. So it won't take more chlorine dioxide. Even if you put more, it won't really react much. So when you do that, if you go for a too high kappa factor, your total chlorine dioxide charge increases. And usually you're not able to keep that low chlorine dioxide charge in your D1. So if you use a lot of chlorine dioxide in your first chlorine dioxide stage, you really cannot compensate that much. So you cannot use that low charge in the D1, mainly because you need some brightness stability, and sometimes you need to get rid of shides. And for that, you need not that low D1 stage dioxide charge. So here we have just a case from the literature to show to you. So here we have the kappa factor from 0.15 to 0.30, your unit kappa 10.5, final pH 3, 90 degrees Celsius, 120 minutes, which is pretty common for D hot. So here you look, as you increase your kappa factor, you see that you increase your brightness. You increase your brightness a little bit more, and then you increase a little bit more. And your kappa number, it decreases as you increase your kappa number. But interestingly, you look that from 0.15 to 0.20, you get a really large brightness increase, but then you really don't get much brightness increase after it. So here's less than 1 point brightness. And here you have almost 2 points of brightness from 0.15 to 0.20. So it kind of stabilizes after certain Kappa factor. So when you look at your Kappa factor, here's how much chlorine dioxide you put as you increase your Kappa factor. So for example, from a Kappa factor from 0.20 to 0.30, you increase more than 3.5 kilograms per dry ton. So that's a lot of chlorine dioxide. And you see here that this extra chlorine dioxide doesn't give you much brightness. So you put lots of extra chlorine dioxide and your brightness kind of levels off. Here's a second study. So here you have a Kappa factor from 0.10 to 0.25, inlet Kappa 10, final pH 3, 95 degrees, 120 minutes. So here, as you increase your Kappa factor, you also increase your brightness and you decrease your Kappa number again. But as you increase from certain point here, you don't get much brightness increase. You see here that you have more than 2.5 brightness points, and here you get only 1 point brightness and then 1 point brightness again. So this means that, for example, increasing your charge from 5.1 to 8.6, you get only 2 points of brightness. So that's a lot of extra chlorine dioxide and not much brightness gain. So here you have another study. So your Kappa factor from 0.12 to 0.20, your inlet Kappa 9.4, final pH 2.7, 90 degrees Celsius, 120 minutes. Again, as you increase your Kappa factor, you increase your brightness and you decrease your Kappa number. But look here again, when you go from 0.16 to 0.20, that's only 0.5 in ISO brightness. So that's almost nothing that you get in return as you increase your charge. So, but here it's a little bit, you can say it's significant from 81 to 82.5. So here what it means in chlorine dioxide charge. So for example, from 0.12 to 0.20, you get 2 points of brightness, but you increase around 2.5 kilograms per dry ton of chlorine dioxide. So that's a lot, only for 2 brightness points. Here's another study, Kappa factor from 0.10 to 0.30, 11.7 Kappa number. Here we don't have a really the hot temperature, but it's just for example. So again, as you increase your Kappa factor, you see that you decrease your Kappa number and you increase your brightness, but again, it kind of levels off as you get to 0.22, for example. So this means that you increase your chlorine dioxide charge and you almost get nothing of brightness in return. So from 8.8 kilograms of chlorine dioxide to 12, you get 0.4 in brightness. So that's really low. So the conclusion is that usually brightness starts to level off as you increase your Kappa factor. So this means that you're having low lignin removal and or brightness, so you're not increasing your brightness. And you know that only lignin affects brightness, so XA does not affect brightness. But you see that your Kappa number continues to decrease. So if you're not increasing your brightness, but your Kappa number is still decreasing, this means that you're still removing XA. So XA continues to be removed. This means that this is actually an excess chlorine dioxide charge. So this means that you're removing your XA with chlorine dioxide, which is not the objective of a dehot stage. When you dose the right amount of chlorine dioxide, only a very small portion of your chlorine dioxide reacts it with XA. So don't put that much chlorine dioxide because you will be only removing XA, and you should not remove XA with chlorine dioxide. You should remove it with your acid hydrolysis at very high temperature. Here is an analysis of the previous studies that we've seen. So one of the studies in that Kappa 9.4, the authors tested these 3 Kappa factors. The authors selected 0.12 as the optimum Kappa factor. And from our analysis, we can go back again and see that from 0.12 to 0.16, that's very good Kappa factor already. So here from 0.12 to 0.16, you have a really good, still good brightness increase. So you can, the optimum is around here. So the second study, inlet Kappa 10, there are four Kappa factors here. The authors did not select an optimum, but when we look graphically, we can see that the optimum is around 0.15 to 0.20. But what you need to have in mind is that your optimum Kappa factor is the one that's going to give you your total chlorine dioxide charge the lowest possible, and also the lowest possible total active chlorine charge. So again, inlet Kappa 10.5, different Kappa factors. The author selected 0.25, but if we look again, you see that the optimum should be around 0.18 to 0.22. Here's Milanese and Colodetti. Okay, here. So the author selected 0.25, but if you look here, there's not much brightness increase from 0.20 to 0.25. So basically your optimum should be around here. You're still decreasing your Kappa number, but this should be mainly due to XA removal. Okay, let me get there again. Okay, and finally, 11.7 Kappa number. The optimum of the authors was 0.22. If we look graphically, you're going to see that the optimum should be around 0.20 to 0.24. This will give you at a maximum 3.5 Kappa number. And it's when your brightness starts to level off. But again, your optimum Kappa factor, you should be looking at your total chlorine dioxide consumption and your active chlorine consumption. Here's an example from the previous studies, how you select your optimum Kappa factor by selecting optimum distributions between D hot and D1. So here's an example. As you increase your Kappa factor from 0.12 to 0.20, here we can see that you get 91 brightness. So it's the same brightness for the 3 Kappa factors. You get higher viscosity at the lower Kappa factor. And what you see here is that the lowest chlorine dioxide and your total active chlorine charge is with 0.12 Kappa factor. So for this example, the optimum should be really 0.12 because it's the one that gives you, for the target quality, the lowest possible chemical consumption. So here's how you find your optimum. You should look at the Kappa factor and the one that gives you the lowest consumption for the same quality. So here we have the Kappa factor from 0.10 to 0.30. If you use 0.10 Kappa factor, that's too low. You can see here that your EP Kappa number is too high, 5.5. Remember that you need a maximum 3.5 Kappa number. So your brightness is too low at this Kappa factor. As you increase your Kappa factor, your brightness increases a little bit, but still a too high Kappa number. So as you increase your Kappa number, you see that when you get to kind of the optimum Kappa number is when you have lower than 3.5 Kappa number. So you get the highest brightness here, 91.3. And this is basically, this is the same consumption. So the authors just kept constant total chlorine dioxide charge. So they just changed the distribution. So here you're gonna see that the best Kappa factors are around 50 to 61% of proportion of your chlorine dioxide to the D hot stage. So your optimum for this example is when you're 50 to 61% charged to the D hot. So here in the first example, your optimum is around 43%. So this is a much lower Kappa number, and this is a much higher Kappa number, is 11.7 Kappa number. The first example is 9.4. So usually when you have higher Kappa numbers, you tend to need a higher Kappa factor. It's gonna be your optimum. Okay, so we talked about the Kappa factor, so let's discuss the final pH of the D hot stage. So let's see how the final pH impacts brightness. So if you look here for different Kappa factors, your maximum brightness is around final pH 3 to 3.5. 2.5, you have a little bit lower brightness, and also 4.5. So the optimum pH is around here for brightness. So here's how your final pH impacts the EP Kappa number. You can see here that if you go to a pH 4.5, that gives you a too high Kappa number. As you decrease pH, you decrease your Kappa number. But look here, when you decrease from pH 3 to 2.5, you get basically the same Kappa number. So from 3.5 to 3, you get some extra Kappa reduction, but from 3 to 2.5, you get really nothing in return regarding the Kappa number. And also your final pH. If you go for a too low pH, 2.5, it really damages your pulp, so you get lower viscosity, and the highest viscosity is around 3 to 3.5 final pH. So this final pH gives you good Kappa reduction, very high brightness, and high viscosity. So your optimum should be around here. So as I told you, the effects of decreasing the pH from 3 to 2.5, you get no return in decreasing the Kappa number, so there's no impact on lignin or X-ray removal. You get lower brightness, so as you decrease your pH, you get lower brightness because chlorine dioxide species are not suitable for brightening at this too low pH. And you also get lower viscosity. So this is what you shouldn't do. You shouldn't decrease that much your final pH, because you get lower brightness, not much more lignin or X-ray removal, and you get lower viscosity. So you get lower quality, you get lower brightness, and no impact on the kappa number. So that's a bad call to decrease your pH that much. And if you increase your pH from 3 to 3.5, you increase your kappa number, so you get lower lignin or XA removal here. So you increase your kappa number. You get higher brightness, but it's pretty much the same here. So you get very high brightness in 3 or 3.5 pH. And the viscosity is pretty much the same at 3 to 3.5 pH. So your D-hot final pH basic rules, so your minimum should be around 2.5. So you should focus on the lignification, X-ray removal, but you should ensure some brightening action. So pH lower than 2.5 gives you poor brightness action, so you should avoid that. And also you should avoid viscosity impairments that happen at pretty much low pH. So you know that you shouldn't decrease your pH that much, because you don't have much lignin there. So there's no need for too much delignification. So you don't need chlorine, unlike softwoods, because in softwood bleaching you get really low D0 stage pH, so you can get high delignification. Also, your maximum pH should be around 4. You should be careful because you need to achieve sufficient delignification, your EP kappa number, maximum 3.5. And you should ensure a very large removal of XA, which is your goal in your D-hot stage. So your optimum pH, the challenge is to remove lots of lignin and XA, but also to brighten the pulp without causing severe pulp degradation. So you should balance delignification, XA removal, and brightening. Also, your chlorine dioxide should be the lowest possible, but you should achieve your target quality. If you go for a too low final pH, you get too low EP kappa number, you get viscosity impairments, you don't get much brightness gain, and then you're going to increase your chlorine dioxide consumption, and also your acid, could be sulfuric acid consumption. So that's not very good. But also, if you go for a too high pH, you get insufficient delignification, XA removal, you get too high post-extraction kappa and low brightness. You need more delignification and brightening in your EP and D1 stages. You increase your chlorine dioxide charge because you need to put more chemicals in your D1, and you may compromise final quality because your final pulp will have lots of XA content. Talking a little bit more about XA removal, we have an example here of an acid hydrolysis stage, not a D-hot. If you start with 60 XA units, here's how the pH impacts your XA removal. So as you see here, when you're at 95 degrees Celsius, you get a bit higher XA removal, which with pH 2.5, and then it kind of levels off. With 90 degrees Celsius, you get pretty much the same XA removal at 2.5 and 3, but then it decreases sharply from pH 3.5 to 4. And also, when you go to a too low final pH, there's a very harmful impact on pulp viscosity. So with 95 degrees Celsius and 2.5 pH, you get lots of viscosity loss, and also with lower temperature, still very high viscosity loss, and your viscosity loss decreases as you increase your final pH. So you get the lowest viscosity drop at pH 4. So the summary is that at 9 degrees Celsius, you get poor X-ray removal at pH 3.5 and 4, and your maximum X-ray removal is at pH 2.5 and 3. When you go to 95 degrees Celsius, your X-ray removal is really high. Then it levels off, but remains high from pH 3 to 4. And pH 2.5, it leads to unacceptable viscosity loss at 90 degrees Celsius or 95, it doesn't matter. It's really high viscosity loss. So there's no need for it to go to 2.5 pH. Here's an example. If we think about selectivity, for example, your delta Xa divided by your delta viscosity here, we have the highest selectivities at higher pH. So your lowest selectivities are at very low pH. And you see here that your optimal pH for good selectivity, so very high Xa removal without losing too much viscosity, is at pH 3 to 4, run at 95 degrees, sorry, here. So the higher, the better the selectivity. So here's very good selectivity. Or you can go at 90 degrees, you can go to pH 3. That's very good selectivity as well. So a final pH from 3 to 3.5, which is good for Xa removal and not too harmful for pulp viscosity, is also very appropriate to balance some delignification and brightening, because you get really balanced with chlorine dioxide species, you get some delignification species, some brightening species. So this is a good pH for delignification and brightening as well. Still talking about Xa removal, the temperature, as you increase the temperature, you remove more Xa. So at 85 degrees, your Xa removal is really low. As you increase your temperature to 90 degrees and 95, you get a higher Xa removal. But you can see here that at pH 3.5, an increase from 90 to 95 degrees, it really increases sharply your Xa removal. Also, your temperature, as you increase temperature, you kind of increase a little bit your delta viscosity, but it's not too much, only a little bit. So you can see that the temperature is very good for increasing Xa removal and not too harmful for pulp viscosity. So as I said, Xa removal increases sharply with increasing the temperature. 90 to 95 degrees is very good for high Xa removal, and there's little impact on viscosity. However, there are some papers or the literature reported some higher viscosity losses at 95 degrees Celsius, but you should look at case-to-case basis. So when you have some trouble in your dehot stage, usually you're looking at inadequate Kappa factor. So you should look at your Kappa factor to inlet Kappa relationship. You should monitor your washing effectiveness ahead of the dehot. You know that carryover consumes additional chlorine dioxide. Usually you are far from optimal final pH. So You should look at lignin and X-ray removal and brightening. So if you're at the wrong pH, you're really in bad shape regarding brightening. So high chlorine dioxide charges may cause a too deep drop of the final pH, and you need high temperature for high X-ray removal. So second bleaching stage, your EP stage, your conditions for optimization, your peroxide dose, your temperature, and your final pH. So as you increase your peroxide dose, you increase your pulp brightness, but you see that if you increase that too much, the brightness levels off, so it's not very good if you increase too much. Also here, where if you increase from around 2 to 4, you get a really good brightness increase. Here's an example that you can see that increasing your peroxide charge, you get higher brightness. It kind of levels off at 4.5 kilograms per dry ton. Usually you get 1 point brightness per kilogram of peroxide that you add. But you should look at your viscosity as you increase your peroxide charge. So you should be careful. So peroxide dose is a balancing act. Your basic rules for peroxide dose, you should react to zero residual. So you should monitor your peroxide residual to the D1. It consumes additional chlorine dioxide. You should have high enough temperature and pH to trigger peroxide consumption. Your minimum is around 2. You should save chlorine dioxide, so don't put a too low charge, maximum around 5. So you should avoid overdosing and viscosity impairments. Your EP temperature, the optimum is around 83 to 87. Usually get a really good brightness increase and reduced kappa number. You should have that high enough temperature to have high peroxide consumption for the lignification brightening. You have high lignin solubility at this high temperature and a minimal impact on viscosity. So you can increase your temperature and don't look at the viscosity because it won't be affected. But you should keep temperature under 90 degrees to avoid very high peroxide decomposition that causes pulp degradation. Your final pH from 10.5 to 11.5, a minimum 10.5 to ensure enough extraction. Above 11.5, there's no increase in brightness and it impairs your viscosity. So in your EP stage, if you might be in trouble if you have too low final pH, you should be careful with acid and chlorine dioxide carryover from the hot stage. If you have a very high peroxide residual, this is mainly due to overdosing. Look at your final pH and your temperature. Also, if you have too low temperature, you're wasting your peroxide charge. You have low solubility of lignin, and you have you might be having peroxide decomposition. So you might have high metal content, too high temperature, or too high pH because they trigger peroxide decomposition. So your D1 stage. So here's the conditions for optimization. Your chlorine dioxide dose from 2 to 5.5 usually. You have your EP kappa number, your brightness and your target brightness. This is how you're going to dose your chlorine dioxide. This is highly dependent on the final pH, temperature and residence time, because this will interfere with the consumption rate of chlorine dioxide. You need higher charges and higher residual when dealing with chives. Final pH is around 3 to 5.5. Usually go 3 to 4 if you want more delignification, chive removal, 4 to 5.5 for brightening. And your temperature from 70 to 85. If you need chive removal, so if you want to remove chives, you get lower temperature. This will increase your chive removal. And if you get higher temperature, this is very good to increase your brightness, but you should maintain a chlorine dioxide residual And this will give you higher brightness stability. And you can go up to 80 degrees Celsius without impact on viscosity. So troubleshooting in the D1 stage, you'll be in trouble if you're far from your optimal pH. So if you use too much dioxide, this will cause a too deep drop of your final pH. Be careful with excess caustic addition for pH control. You should monitor also your washing effectiveness of a handle, the D1, because if you have lignin carryover or peroxide carryover, this will consume dioxide. So we also be looking at inadequate chlorine dioxide charge. So you should look at your initial residual, your final residual, and maybe if you lost some consistency. And you should look at your dioxide charge versus your temperature and residence time, because if you use higher temperature, this you consume more dioxide, or the opposite also true. And if you use too low temperature, this you won't get much brightness gain. So when we look at bleach blend optimization, there are some challenges in bleach blend performance. So bleaching reactions are non-linear and highly dynamic. There are long delays in the bleach blend, so very long residence time. So there are many variables and very complex variables for each bleaching stage, as we've discussed earlier. We know that chemical requirements to reach your desired brightness can vary significantly from mill to mill. Even mills using similar technologies, equal bleaching sequences, you can observe a wide variation in performance. And those performance variations can derive from many factors. You know that each mill is unique, different wood, design, equipment limitations, operating conditions, quality specifications. But the goal is always the same, pretty much. You want to get minimal chemical cost, maximum production, you want on-target quality. And how do you get that? You have to combine the addition of bleaching chemicals, operating conditions, and you should do it at all stages. And of course, you should combine all stages as well to minimize the cost while achieving your target quality. And also the process operating conditions, they should be at optimum targets in each bleaching stage. And who's going to do that? Who's going to keep that continuous optimization at all times? The mill operators, they are the guys that are there 24/7. So sometimes you have your expert operator. He's well-trained, experienced, focused. He makes the right move at the right time. He has an eye for optimization. This is very good. But then you have shift changes. So when you change shift, if you've been in a mill, you know how it works. You lose a lot of information and tracking of your process when there's a shift change. And the relief operator, he's not that good. He's not an expert operator. So he has less information already. Sometimes he's still in training. He has less experience. Sometimes he's distracted with other tasks. The night shifts are tough. There's some fatigue. People are tired. So it's tough to keep optimization at all times. So even the best mill operator is not available to focus only on process optimization 24/7. Also, process engineers, they're not there running the process. They're not there operating. They're only for support, and they're not full-time at the mill. So how to ensure that the bleach plant is running at optimum targets, seeking continuous optimization, and also how to ensure that the right adjustments are made for many varying upset conditions, still to minimize the impact on cost, quality, and production. So this is why you have advanced process controls to help you ensure that. So here at Valmet, we have the Valmet Bleaching Optimizer that will help you with that. So with Valmet Bleaching Optimizer, you get remarkable bleaching chemical savings, you get stable on-target quality, so you get basic stabilization of bleaching, advanced quality control, a lot of adjustments in the process, so you get lower variability in your kappa number, in your brightness. You can optimize your brightness to maybe a lower target if you don't get that much variation, and you reduce your chemical consumption. So it's what everyone at the mill wants. So with Valmet Bleaching Optimizer, there's a lot of we have a lot of success cases. For this example, 30% reduction in final brightness standard deviation, 10% of savings in chemicals, and so the optimizer is usually combined with, for example, kappa analyzers, dirt count, for example, Shive analyzers. You get the Valmet Chromac, which is for brightness. You have the Polarox for residuals. You get filtrate pistons, for example, for pH probes. So usually when you want to acquire a Valmet Bleaching Optimizer, this is what you're looking for. You get high pulp quality, so low brightness deviation, strong pulp, low dirt count. You get and you want low bleaching chemical costs. You want to have an environmentally friendly process. And the main challenges, as I told you before, is that the final brightness is difficult to keep at the target. You've seen a lot of variables that affect brightness, so it's really tough to optimize. So sometimes you get too high variation, you have strength losses, shives, chemical consumption, production changes, time delays, long process delays. You have your operators, human errors, and you have different operation between shifts. So with your Valmet Bleaching Optimizer, you get production rate control, you get real-time optimization, cost calculation. You can manage a lot of changes in production, grade type, species. You have, for example, some features like your retention time estimator, pulp tracking. You can monitor the quality and optimize the quality of all your bleaching stages. For example, in your D-hot, you get the Kappa Factor control, your EP as well, brightness control, chemical dosage, temperatures. So it's really a very good advanced process control to improve your bleach plant. For example, we have here some specific controls for the hot stage. You look at your kappa target, pH targets, you get production, pH, you monitor your residuals, temperature, you get all the measurements here, Chromac brightness, kappa analyzers. You can combine all of this into the control to get stabilized pH conditions, reduced kappa, and brightness variation, and you optimize your chemical consumption. So basically, at a D-hot stage, the control strategies is you get a Kappa Factor analysis, a Kappa Factor control, a feedback from your EP number, EP kappa number and brightness. There's some feedback for unknown or unmeasured disturbances, production rate changes. You have your final pH, you get your acid dose right, you also include the carryover, and you have a kind of H factor for a temperature control. In your EP stage, the control includes the peroxide dose, final pH, your temperature, so all the variables that we've discussed. In your D1 stage, also you get all the brightness measurements here, pH measurements, temperature. So as a result, when you implement and you use the bleaching optimizer, you get more steady and stable pH, more stable residual, reduced brightness variation, and optimized chemical consumption. So in your D1, you get your chlorine dioxide dose, the final pH, the temperature. So you look to optimize all the variables that we've been discussing. So the optimizer uses multiple variable control. So it controls the process as a whole, uses multiple inputs, information. Targets are continuously optimized, pH targets. You get more flexibility in finding optimal control solutions. So you're always looking at the optimal targets. So this optimization takes advantage of all the process variables for optimization. So what you want is lower chemical consumption at target quality. You have real-time optimization. So optimization across all stages, management of changes, residence time, real-time cost calculation. So it's a very complete system. So the results: reduction of quality losses, easy operation. So you get controls for stabilization, brightness control, kappa number, pH. So you get your target quality with lower variation. So in the end, you get lower variation in your quality, lower chemical consumption, and is what you want. You want chemical savings at high quality. There are some examples here of success cases. Final brightness reduced, total consumption reduced, control 95% operating of the time, chlorine dioxide reduction, caustic reduction. So there's a lot of success cases. Chemical cost reductions, easy process changes, species changes. Some very complete optimization tool. So that's it. Sorry that I took too long. It was a lot of information, but I'm open for questions.
No problem at all, Bruno. Thank you for the excellent talk. It was very informative indeed. And now we have some questions from the crowd and still some minutes left. So let's go to the first one from Daniel Lima. He said, hello, Bruno. When we increase brightness in the D-hot stage, what problems can I have to the next stage, the EP1? He says that actually if brightness increase, he believes that the viscosity is decreased.
Okay, thank you, Daniel, for the question. Yes, actually, that's why you shouldn't work at a too low pH or a too high Kappa factor in your D-hot stage, because you're going to lose a lot of viscosity. So the hot stage is not as selective as the D1 stage. So you should be careful not to increase your brightness too much. That's why you need to find the optimum distribution between the D-hot and the D1, not put too much in the D-hot stage to preserve your strength.
The next question is from Marcelo Cura, also a student from the Federal University of Viçosa. She says, thanks for the lecture. Why do oxidizers that operate in alkaline media, such as oxygen and hydrogen peroxide, have little effects on excess?
Yeah, they have little or no impact on XA. Actually, at very high temperature, there's some effect, but I really don't know exactly the chemistry right now, but they are unreactive. XA are unreactive towards those oxidizing chemicals, but the chemistry behind it, maybe there are people at the university that can help me with that.
There are some questions, Bruno, according to the generation of effluents. The first one from Caio Michelino. He says, good evening, Bruno. What is your suggestion in combating the large generation of effluents in bleaching? Is it possible not to generate or to reduce these effluents?
Um, uh, Thank you for the question. With a dehot stage, and so you already have a lower environmental impact. But if you look at bleaching as a whole, you cannot really get zero AOX generation or zero effluents. You could maybe think about using some of your EP stage filtrate, for example, for using wood yard or something, but you cannot get to zero. But if you use hot chlorine dioxide stages and you use proper distribution between the stages, you already have lower environmental impact.
Actually, I have a question about this topic
Sure.
because the removal of exynoic acids from the pulp may not be interesting due to the generation of effluents. For me, it gets more important to say about it when we're talking about the eucalypt, as you said in your lecture, because there is a bigger amount of these exynoic acids being generated. And then to remove them, you have a consumption of chemicals and loss of iod. So is there any technology maybe involved in development to hide the chromophoric characteristics of exynoic acids and keep it in the pulp? Not to remove it, but just try to hide the effect and not generate these effluents.
Yeah, that's interesting because if you remove it from the pulp, then you have it in your wastewater, in your effluent. So it should be interesting, but I'm not very familiar with ways to just modify your XA and not remove them at all. So because their chemistry with chlorine dioxide and chlorine and hypochlorous acid, there's a high degradation of XA. But it should be interesting if you could just kind of modify them as you do with some lignin. If you could do that, just modify them, and so they don't give you much brightness reversion. Or maybe you could modify some bleaching stages just to improve your brightness stability, so you don't have to remove that much excess. That would be interesting, of course.
Still in this topic, a question from Claudio Silva. He asks you to comment about the quantity and the quality of the effluents in this three-stage bleeding sequence that you were talking about in the lecture.
Um, well, with hot chlorine dioxide, the lignification, the effluent generation is usually lower than with regular D0 stages, but the generation is also a little bit a function of your kappa factor. If I'm not mistaken, at higher kappa factors, the AOX generation is also a little bit higher. Um, so that's why I do not recommend very high kappa factors. I've not commented on AOX generation because it's a confusing topic. It's not, there's not too much truth about it. A lot of people say different things, but usually if you increase your Kappa factor, I believe that you get higher AOX generation, if I'm not mistaken. So that's why I do not recommend a very high Kappa factor.
Sure. Now going to another topic about the bleaching. Another question from Daniel Lima. He says, hello again, Bruno. What level in the tower D-hot would be optimal to achieve a good performance?
What level?
Yes, I guess about the height.
Okay. The level, it will vary from mill to mill. He's saying if you have an upflow then downflow tower, of course, that you work with a level like a bleaching tower. In this case, you should really calculate to have 2 hours, 2 to 3 hours. You should keep your level in a way that you can maintain 2 to 3 hours of residence time. If you have lower residence time, this will affect your X-ray removal. And if you have too long residence time, it's going to be tough to control pulp degradation. So that's why you should try to keep it 2 to 3 hours so you don't get lost with quality.
Bruno, I have another question, maybe
Sure.
a little bit out of the scope, but just for curiosity,
Sure.
because for grasses, the hot is also used many times in the beginning of the sequence. So I'd like you to comment a little on grass bleaching and what about the difference between this kind of material for bleaching and the wood in general?
Can you repeat the question? Which kind of bleaching?
For grasses, like sugarcane, bamboo.
I've never worked with bamboo or other kind of wood types, but what you have to look in those bamboos and similar is how much lignin they have and XA, of course, after pulping. So if they have a very high XA content, it should be interesting to go over a D-hot stage. So that's the basics. But you should look at pulp viscosity as well, because the D-hot is very aggressive. So depending on your XA content, you should go. You maybe go with a regular D0 stage.
I guess also to point that the content of Exynoic acids is lower.
It's lower. In this case, it shouldn't be advantage to use a D-hot stage, as it would be for softwoods that you have a very low XA content. So a D-hot stage will maybe actually increase your dioxide consumption, because the D-hot stage is not very good for brightness increase. So maybe you should go with a regular D0 stage and get more brightness.
Sure. Then we have a last question from Bruna Virginia. She congratulates you on the presentation and says, what do you think of the acid or alkaline leaching between the bleaching sequences?
About alkali leaching, you got to maintain a very high pH. So to get a high lignin solubility to get this leaching effect. But for the acid stage, there is some lignin removal just because of leaching. If you use an acid hydrolysis stage, even without chlorine dioxide, there's some lignin removed only with some leaching effects. And then with alkaline extraction, that leaching effect is much more pronounced.
So I guess it's all we have. Thank you once again, Bruno, for attending our invitation to be here. I know that it's been difficult weeks for you. These times of changes is always with of a lot of things to do, and even though having other personal issues to deal with, you accepted very kindly and is here with us almost for 2 hours to share all your knowledge with us. So thank you very much. It's been a great pleasure to have you here. Hope to see you
Oh,
again in other seminars.
sure. Thank you. It was a pleasure to me. Thank you very much. See you next time.
And just some information before we close the session. Tomorrow, our lectures will begin in the morning. So we have two starting at 8:30 a.m. in São Paulo time with Clarit Azerhat talking about cellulose nanocrystal production and applications. And then at 10 a.m., we have Mikhail Balakshin talking about lignin from fundamentals to applications. It's always great to remember for all the registrants that are watching us from abroad that the Greenwich Mean Time of Brazil is -3. So just keep in mind of that, the time zone, and you are not going to miss the last lectures of our seminar. Thank you very much for all of you, mainly for those in Europe that you know that are in the middle of the down watching us sharing this knowledge about bleaching. Hope to see you again tomorrow. Good night and stay safe.
Bye bye. Thank you.